At the University of Toledo, we are surrounded by experts. And we tap into those experts here on Rocket Talk.
This past summer, NASA seemingly stole the script from Hollywood. In preparation for a worst-case scenario of an asteroid barreling toward Earth, NASA set out to test our ability to change the trajectory of the asteroid Didymos. This was done through a double asteroid redirection test, better known through its acronym DART. Here to give us a deeper understanding of NASA's effort is Professor of Astronomy, Dr. Tom Megeath. Thanks for being here, Tom.
Oh, it's a pleasure. It's a pleasure.
Okay, so I'm going to go to the paper here for a second because I want to get these specs right. But based on my initial research, I see that Didymos is about half a mile wide, 6.8 million miles away, and traveling over 14,000 miles per hour. And NASA hit it with a rocket. To those of us who are lay folks, this seems like a pretty impressive feat. Is it to you in the field?
Yeah, well, I'm not an expert in asteroids. I study more distant things. But, consider this. They hit it within 17 meters. That's like 50 feet. And it's what 6.9 million miles away. So that's literally like hitting a bullseye on a dartboard from 15,000 miles away, right? So that's impressive. And it's even more impressive than that for this other reason. It takes like a minute for a radio signal to go to the satellite and back, right? So nobody could sit there controlling it with a joystick. It had to do it itself. And even that makes it even harder is that when you look at the asteroid from the Earth, it's just a tiny speck of light. The satellite was the first thing that could actually separate the system. So Didymos is a moon of an asteroid that orbits the asteroid Didymos. And it was the satellite that for the first time could actually separate those two. And so it had to separate it on its own, figure out where to go, and hit it to within 50 feet. And it did that, going at 14,000 miles an hour. Right, so that's an impressive feat.
Yeah, no doubt. So, there's the why and there's the how here.
Right.
Tackle those in whatever order you want. Why is NASA trying to do this, and what were kind of the specifics of the mission that that led to this success? Right.
So this is basically a laboratory experiment, and the issue here is if we found an asteroid that was heading toward the Earth, right? So Didymos is about 140 meters, about 500 feet across, right? If that hit the Earth, it could destroy a large city, right? It can just completely wipe out, kill millions, right? So if we actually detected one, could we actually change its course, right? So what NASA did was a simple experiment is they just splatted a spacecraft into this asteroid. But they chose a very specific asteroid because it was actually the moon of an asteroid going around the other one. And because of the way it went around, they could measure its orbit, the orbit of this moon around the asteroid very accurately. I can talk about that later. And so this allowed them to precisely see if they slammed this spacecraft into this asteroid, how much could they actually change its motions? Right?
So, but if an asteroid's heading towards Earth that doesn't have one of these moons orbiting around it, or does that...
It actually, yeah. So the asteroid heading to the Earth doesn't have to have a moon. It could just be a single asteroid. What the moon allows is it creates a laboratory where we can measure this very accurately. Because what they actually wanted to do was measure if we could change the orbit of the moon. The moon goes around the asteroid every 11, the Didymos, the moon of Didymos, this is sort of complicated, goes around every 11 hours and 55 minutes. And we can see this because if you watch it with a telescope, you can see the brightness of Didymos go up and down as the satellite travels into the shadow and back. And so you can measure its orbit very precisely, right? And that's what NASA needed because this small spacecraft isn't going to change the orbit very much, right? And so we slammed it in there. We wanted to measure we wanted to see what would happen. Right? We just wanted to smash an asteroid. And the reason this is interesting is that asteroids, we think of them as rocks, but they're actually what we call rubble piles. They're a bunch of rocks held loosely together by gravity. And so if you smash it, it's not clear exactly what that's going to do, right? And how much change your spacecraft is going to impart into the asteroid. So if you hit it, is it going to change the orbit enough that it doesn't hit the Earth? Or is it going to, just nudge it slightly and,
Well, we'll get to that in a second here about, whether or not it worked. But how do they do this? Just put a rocket on a launch pad and send it on its way, or?
Yeah, so there's basically a satellite, right? It's called DART. And they launched DART from, actually it was a Falcon 9, a SpaceX rocket ship, I think about a year ago. And it just slowly made its way over to that. It actually had like what's called an ion electron engine and solar panels, and it had a camera so it could actually figure out where it was. And they navigated it over to the satellite, and then basically they just used the natural orbital motions both of the moon coming around Didymos and the motion of the satellite to create sort of a combined velocity of 14,000 miles an hour.
Okay, so did it work? Are we safe now?
Well, are we safe? Actually, so they said that maybe we'll be able to reduce it by maybe a minute or so.
Reduce what by a minute?
The orbit. So let me back up a minute. So they have this Dimorphos goes around Didymos every 11 hours and 55 minutes, right? And so they wanted to see if they could change that, slow it down a bit, right? And so they thought it might change it so that instead of going around every 11 hours and 55 minutes, maybe be 11 hours and 54 minutes, and they can measure that. They slowed it down by 32 minutes. So they made a significant impact. And the reason is when the satellite smashed into Dimorphos, it created this huge blast of debris that's now extending 6,000 miles from that. And that debris acted like sort of like a rocket exhaust. And so it slowed it down even more than they expected, right? So this is actually sort of good news. If you hit a satellite, if you hit like a big rubble pile asteroid, bunch of rocks coming at the Earth at like high velocities, not only do you get the impact of the spacecraft, but you create a blast, and that blast actually slows down or deflects the asteroid even more.
I mean, this is probably the stupidest question for someone. Why not just put a bunch of explosives on the thing and just blow it up when it hits?
Well, so first the energy of just the impact is huge, right? So it's not clear, there's already a lot of energy just from the impact itself. The other thing is you don't want to just blow up the asteroid, because then you just have a bunch of asteroids hitting the Earth at the same time, right? You want to figure out how to deflect its motion, right? And so this is the simplest thing, is just to slam it with something. You can think of like more complicated ways of doing that later, but this is a laboratory experiment, and you start with the simplest experiment first.
Okay.
Right?
So if this asteroid were on a trajectory to Earth, would it now not be based on what they've done, or do we just have proof of concept?
This is basically a sort of more of a proof of concept. We're trying to figure out how we could deflect it, right? So there's two parts to this. First is finding them, and NASA is engaged in efforts to find all the potentially hazardous asteroids which may hit the Earth. And then the second thing is, if you find it, how do you deflect it, right? So this is just literally an experiment to figure out, can we deflect it, and what do we need to do to deflect it?
I want to ask about the first part of your question there. So an asteroid's surveying to see, what might be out there heading towards us. Is this something that should keep us up at night? Should we be worried about asteroids heading towards Earth?
Well, at the moment, there are no known asteroids that are potentially hazardous.
No known. What percentage of the sky?
Well, of the ones that are the size of Dimorphos, which are about 140 meters, maybe about 40% are known. Oh, okay. And so the goal of NASA is actually directed by Congress to find 90% of those in the next few years, the next decade. But just to give you a sense of the urgency of this, so if you go back to 2013, over Siberia, a smaller asteroid, actually sort of a giant meteoroid, about 20 meters, exploded over Siberia, and it injured 1,500 people, right? So that's a 20 meter, 60 feet. If you go to something the size of Dimorphos, it could take out, if it hit the right spot, it could take out a whole city. And so in 1908, again in Siberia, I don't know what's always Siberia, Tunguska, there was basically this large explosion in a very remote area of the Earth. And it took people, scientists, decades to figure out what happened, but basically an asteroid exploded and it flattened trees for hundreds of thousands of miles, right? So this is something that could happen, but it's preventable. It's basically a preventable apocalypse. We can stop it.
Well, and if we go back even, millions and millions of years beyond that, right? This was the thing that likely caused the extinction of a lot of things.
Right. So 65 million years ago, something about 8 kilometers hit the Earth, and it caused the extinction of the dinosaurs and probably darkened the planet for decades. And so, this is an apocalypse that we could stop. We don't have the technology right now, but it's reachable. And so we need to find them, and then we need to figure out how to deflect asteroids that are coming toward the Earth.
Kind of a tangential question here. I mean, and I know it's been playing while we've been talking here, but there was this really cool video that was making the rounds of the actual impact with Dimorphos. So what was the purpose of that video? Did we actually learn something that we didn't know about asteroids, or is this just great PR for NASA?
No, you need to know. Well, okay, so what's happened? First, that video, that same camera was how it actually found and located Dimorphos, so it needed to figure out where to go. Right, so the satellite used that information. Second, to figure out the impact, so to do the laboratory experiment, you need to know the size and the shape and the mass of Dimorphos. And those images basically are are our best images of Dimorphos. We now know its size, we now know its shape, we now know its mass. The second thing is we have a picture of the impact area of what it looks like. So in 2 years, The Europeans are going to send another mission to the same asteroid, and they're going to look at what we did to it. It's called Hera. And so we're going to actually look and probably see a giant crater. And by looking at that, we can actually, scientists, astronomers can improve their models of what happens, when you slam something into an asteroid.
Well, we'll have to have you back and when that happens to get a sense of what we learned.
Yeah.
Hey, we got about 40 seconds here. What are the other things we need to worry about from outer space besides asteroids? And are anything being done to? I mean, I feel a little, warm in my heart knowing someone's looking out for us in this regard.
Yeah.
Other people looking out for other concerns from outer
Well,
space.
in terms of like mass casualties, asteroids are I think the most, the biggest concern, right? And other things, people worry about supernova stuff. Those are so distant that they won't affect the Earth. Solar flares might affect, communications, but they're not going to lead to like casualties. But asteroids are dangerous, and we need to figure out how to stop and deflect them.
Oh, that's great. Well, thank you so much for being here. We appreciate it. That's all. Sure. That's all the time that we have for Rocket Talk today. I'd like to thank again Dr. Tom Megeath for being here, and I'd like to thank you all for hanging out with us. And we'll see you next time on Rocket Talk.